Hey, welcome back. Today we're going to be going over some general principles of statics, and these are statics principles that are going to be the chapter 1 material for most statics textbooks, most uh, introduction, introductory mechanics textbooks where it's statics and dynamics, and statics is basically just a specific application of dynamics where there is no acceleration and therefore it is either moving at a constant velocity or it's not moving at all. So it would be static in that case, both of those cases. Some basic quantities that you'll need to know for your statics class are length, time, mass, and force. Length is used to describe the position of different particles in space and how the system is shaped. That's really important for the shape of the system. And time is conceived as a succession of events. Time isn't useful in statics, I'm going to be honest. It's useful in dynamics. It's one of the most important unit types for dynamics, but in statics, everything is independent of time, and it's not going to change as time goes on. Mass is not too useful in statics, but since the sum of forces almost always equals 0, but in some specific cases, like when you have a hanging weight, it's like vertical, and gravity affects it, you'll need to know the mass, and not too useful. Force, on the other hand, is going to be very important, and in particular, both length, can't see that at all, length and force are going to be your most important units for statics. Forces are generally just considered pushes or pulls that affect the system, and there are two main ways to perceive forces. There's point forces and there are distributed loads, and a point force is basically just a concentrated load. So if you have a bar, let me draw this in white real quick. If you have a bar and you have a force acting on it, and you're only considering it as being acting exactly, let's say, one meter away from the end, and it's only acting on that one point right there, that's a point load. But if we were to say that from the right end, there is a load, there's a load that acts along this whole area, so this area right here. If it acts on that whole area and it's between like 1 meter and like 3 meters, that would be a distributed load. And distributed loads are more of what we actually experience in real life, but point loads are really good for idealizations and just simplifying your system so that you can do calculations on it. Because if we considered every single small, minute detail from real life, then we would just make ourselves really weary with all the calculations that we do. And some common idealizations are just these 3 idealizations, and we use these idealizations, or you could say simplifications, to make the systems easier to work with and better to use for applying the principles of statics. The 3 main ones that you're going to use are considering objects as particles, considering systems as rigid bodies, and considering forces as concentrated forces. And I have written out here some more explanation of the stuff. Particles, you probably already know or you've probably already used particle simplifications before in high school or maybe even middle school. I think that they're starting to do stuff like that in middle school. So like you have a car and it's on a straight track and you consider it as a particle because it is simple enough and it's only moving in one direction and you don't really need to worry about its geometry. So you just worry about its displacement, velocity, and acceleration, like in high school, physics 1 type stuff. And those are pretty easy to deal with since it's just one simple particle. As the dimensions go up, it gets more complicated, and you might have to rely on rigid bodies instead. So in dynamics, when you have a object that is translating and rotating, then you might have to start dealing with rigid bodies and stuff. Or if you have forces that don't have the line of actions each going through the same point. So a line of action is basically you have a force, and that force goes through to the point. And when those lines of actions, or when you have more than one point, if they don't meet in the same place, then you have to consider a rigid body. And rigid bodies are really useful for more complicated stuff. So if you have a truss system, then you're going to want to do rigid body stuff. And you can't just do particle equilibrium anymore. What else? Rigid bodies do not like flex at all. Like, so you have a bar, right? This bar, it's sticking out of the wall. Put a load on it, put some force on it. It's not going to bend. It's not going to go and like swoosh down to here. It's rigid and it's not going to move at all. So in real life, everything that you will load is going to have some small amount of flex to it. So like if you're sitting at a desk and you push down on it, it's going to flex a little bit. Even if you don't see it do very much flexing, it's going to flex somewhere because that's just what most stuff does. What else? The concentrated forces, as I mentioned earlier, they're useful for simplification, and you can really only use them when the area that the force is applied over, like in real life, is small compared to the actual size of the system that you're dealing with. So if you have a car or like a truck and you're pushing on the back of it with just like one hand, or you're pulling something with just a hook and it's like a big old fish or something, then you can use a point simplification easily, and you'll get accurate results that way. Nextly, I just surprised myself. I dropped something, my bad. Next is the Newton's laws of motion, and you got the first law, second law, third law. You're probably already familiar with this if you're an engineering student and you're watching this video. And the first law is basically objects at rest stay at rest, objects in motion stay in motion. Unless there is an unbalanced force, then they'll accelerate. But first law is important for statics because that's all we're relying on really, is the balanced force situation. And yeah, here's a small little illustration that shows this is like particle, I guess, or like maybe a ball. It's got 3 different forces, each acting 120 degrees apart. And they're supposed to be equal magnitude. It doesn't quite look that way, I guess, but close enough. So the sum of forces equals 0, which means that the acceleration equals 0, and so it's a statics problem. And the second law, let me just erase that real quick. The second law is the big equation that you'll need to know. And it's a particle acted upon by an unbalanced force experiences an acceleration that has the same direction as the force, and the magnitude of that acceleration will be directly proportional to the force. And the way that it's going to be proportional is by its mass. So you just basically divide the force by its mass, by a particle or a system's mass, and you get the acceleration. And right here, we've got an illustration of that. So this particle has mass right here, and it's acted on by a force, and the acceleration is going to be in the exact same direction, and it's going to be to the right. In this case in particular, it's to the right. It's going to be the same way as the sum of the forces every time. And here's the third law. It's kind of self-explanatory, I guess. Each force has an equal and opposite reaction. Each action has equal and opposite reaction, and those are going to be completely collinear. And yeah, it's just something that you gotta know. I got a little illustration here, and then here showing that their magnitudes are going to be the same. Another thing that you're going to have to know is gravity and weight. Gravity is an attractive force, so that means that it's always pulling. It's always going to be pulling. Gravity can't push. It can only pull. It's between two separate masses. That's how we typically see it. It's actually between every single particle of mass pulling on one another, and it's all really messy, I guess. It seems messy, but it's not. But everything pulls on each other, and yeah, it's always attractive. Here on Earth, we experience gravity as pulling us downwards with an acceleration of 9.81 meters per second squared, or in traditional U.S. customary units, 32.2 feet per second squared. And as a result of gravity, we have weight, and we experience it as a force that pulls us downwards towards the Earth. And right here, we have a way to figure out your weight based off of your mass and the acceleration due to gravity. And yeah, the units are extremely important for every problem that you're going to do as an engineer or in science in general. And there's two main systems of units that we have to deal with. There's the SI unit system, which is the International System of Units, and the U.S. customary units. And typically, I'd consider the SI to be simpler to use, and the U.S. customary units to be a little bit more of a pain. But you're going to have to deal with both, so you got to get used to it and just be able to do both. The SI units are based off of the meter, the second, the kilogram, and the Newton, while the U.S. customary units are based off of the foot, the second, the slug, and the pound. And that is always true. Newtons and slugs are both derived from other units within the unit system. So the slug comes from the pound times second squared per foot, and that's just the mass. And the newtons are kilogram meters per... I'm not sure, that's wrong, but I just wrote kilogram something per something. It's derived from those. That's all you need to know. And here's some conversion factors between SI and U.S. customary units that you can use for most of the time. They're accurate enough for most of your applications. Here's some prefixes that you're going to need to know. There's giga, mega, kilo, milli, micro, and nano. And the positive exponents are the ones that mean that it's bigger than the normal unit is, and the negative ones means that it's smaller than the normal one is. Yeah, that's basically it for the units. And overall, in general, some stuff that you'll need to know is that when you're working on engineering problems, the best way to make sure that you have it down and you understand it very well is by working with the problems, like actually solving problems. So in your textbook, you're going to have tons of examples. Maybe not all of them are going to be worked out for you, but there should be examples in there for you to follow along and understand. So what I recommend is looking at the problem statement of the examples, then trying to work it out, then looking back at that example and making sure that your work aligns with the other stuff. And when you're doing those problems, you're going to want to try to visualize it in real life. So going back to the car stuff that I said earlier, you're going to want to visualize that point as like a real thing, and that just, or it helps me to understand the problems better, is to try to visualize them as real life things. When you're working on problems, in statics especially, you're going to want to draw out diagrams to help you. You're not going to want to draw them like really small. So say I have a truss system. You're not going to want to draw it really small and then try to write all of this stuff on there with the different lengths and the forces and stuff. You're just not going to be able to read it if you draw it too small. But if you draw it big enough, it'll be useful. And I'm just going to zoom in real quick. It'll be useful to actually get calculations from it. So you say you got forces here. You know that this is like 6 meters apart or something. You got 100 newtons here, 10 newtons here. You got the forces all over the place. You're going to want to, basically, you're just going to want to draw it big enough so that you can read everything and do your calculations with that visual aid. I can't do problems without being able to visualize them, typically. So it's good to draw them. And as you're doing these problems, you're going to want to work them out in mathematical form. You're not going to just be able to visually solve for everything, because it's not going to be that easy. Like say for instance you have a particle that has forces acting up and forces acting down. Each of these forces is going to have a real number that is associated with it to make sure that you can evaluate it, and just know that you're going to be able to do these things mathematically. And when you're working on problems, if you know that there's equations that you're going to have to use, make sure that you write them out and you have them ready with you. You might want to have a printed out formula sheet as you're working on your homework or something, maybe sort of like an aid to help you do your homework. And lastly, make sure to use your engineering intuition and your common sense to see if the answers that you get when you solve problems make sense. Like, are they reasonable? So if you're trying to lift a car off the ground or something, you're trying to suspend it in air, you should know just by common sense that it's going to be more than 10 pounds to lift it, you know? So if you have a crane that's lifting a car and you end up getting that the tension in the crane is only like 10 pounds, and that's like carrying the entire weight of the car, you're going to know that that's wrong just based off of common sense. And there's plenty of stuff similar to that where you'll get an answer and you'll say, that's not quite right, and you just look at it again one more time and you get a much more reasonable answer. And that's basically it for this general principles stuff. I'm going to post this as a PDF, this thing, and I'll link it to it in the video. And yeah, thanks for watching, and good luck in your classes.